If a central atom has 2 sigma bonds and no lone pairs, then the molecular shape is linear with a predicted 180-degree bond, and this central atom is said to be sp hybridized. So there are 2 sp hybridized orbitals getting as far away as possible linear. What do I mean by sp? Well, an s orbital is a sphere. A p orbital is a dumbbell. And these are just shapes that describe the probability of finding an electron in that space. So in an s orbital, the electron could be anywhere in that sphere. In a p orbital, the electron could be anywhere above or below the nucleus in this nice little dumbbell shape. There are 3 different types of p orbitals: on the x-axis, the y-axis, or the z. So they're actually all together. So the same nucleus is in the center like this, but we separate them out so that you can actually just look at one at a time. So here's our x. If we take a p orbital and an s orbital and hybridize it, we can form 2. So we took an s and a p, we can actually form 2 sp orbitals. These 2 sp orbitals get as far away from one another and form 180-degree bond angle linear. Now these 2 empty p orbitals are actually perpendicular to one another, 90-degree angles, with this hybridized sp orbital. A sigma bond occurs when the electron overlap is between the nuclei of the atoms. A single bond is a sigma bond, a double bond is a sigma bond and a pi bond, and a triple bond is a sigma bond and 2 different pi bonds. So now whenever I talk about electron regions getting as far away as possible, I'm just going to say 3 sigma bonds getting as far away as possible will form 120-degree bond angles, and the hybridization is sp2. There are 1, 2, 3 regions, so S is 1, and there's 2 p's. There's 3 total. sp2 hybridized, 120-degree bond angle, trigonal planar. It's all on the same plane. If there are 2 sigma bonds and 1 lone pair of electrons, then this central atom is still sp2 hybridized. There's 1, 2, 3 electron regions, and the predicted bond angle is slightly less than 120 degrees. This is bent sp2 because there's 1, 2, 3 regions. With 4 sigma bonds and no lone pairs, the molecular shape is tetrahedral with a predicted 109.5 degree bond angle. sp3 hybridized. sp3 with 3 sigma bonds, 1 lone pair, then the predicted angles are less than 109.5 degrees. This central atom is sp3 hybridized. An example of this shape would be ammonia, NH3, trigonal pyramid. If one of these sigma bonds is instead a lone pair of electrons, then the molecular shape is bent. There are less than 109.5 degree bond angles, and this central atom is still sp3 hybridized. dsp3 trigonal bipyramid. Notice you have I've colored the atoms that are axial red and equatorial are green. They are not the same. Notice that there are a 90-degree bond angle between this axial and this equatorial atom, and it's 120 degrees between the equatorial bonds. So the green to green is 120 degrees, red to green is 90 degrees. So there are 2 different bond angles in a trigonal bipyramid dsp3 hybridized central atom. If one of the sigma bonds is replaced by a lone pair of electrons, the lone pair of electrons actually goes to the equatorial position. now we have the expected 120 degrees, but maybe slightly less because this lone pair actually takes up a little bit more space. And then predicted approximately 180 degrees, and we call this a seesaw with a DsP3 hybridized central atom where you have 4 sigma bonds and 1 lone pair of electrons. If you have 3 sigma bonds and 2 lone pairs, then it's DsP3 hybridized because you have 1, 2, 3, 4, 5 electron regions, DsP3. So you'd have 5 DsP3 orbitals getting as far away as possible. 2 are lone pairs, we have a T-shaped. If you have 2 sigma bonds, 3 lone pairs of electrons, then the predicted angle would be 180 degrees linear, DsP3. 6 sigma bonds is D2sp3 hybridized. So 2, 3, 4, 5, 6, so that adds up to 6, we're good. Octahedral, 90-degree bond angles. If one of these sigma bonds is indeed a lone pair of electrons, then it's also D2sp3 hybridized, but it looks like this with a square pyramid. And if you have 4 sigma bonds, 2 lone pairs, this is square planar. Again, D2sp3 hybridized. Now, I don't want you to get confused. This is a square planar molecule. Let's look at that tetrahedral again. A tetrahedral is totally different from a square planar molecule. This tetrahedral, you see the difference? Square planar, it's all on the same plane. Tetrahedral, different, right? Now, let's use the valence bond theory to make predictions about these molecules, okay? This central carbon has 1, 2, 3, 4 electron regions around it, so we know it's tetrahedral sp3 hybridized. We expect a 109.5 degree bond angle. There are no empty p orbitals because all 3 p orbitals were used to hybridize into this molecular shape. This carbon, so notice in this molecule there's 2 central carbons, so we'll just look at them one at a time. This central carbon has 1, 2, 3 electron regions getting as far away as possible, so it's a 120 degree bond angle, sp2 hybridized. So sp2, where we would predict 120 degree bond angles between this carbon and that hydrogen, that hydrogen, that hydrogen, and then that hydrogen and that carbon, where there are 3 sigma bonds and then 1 pi bond. The pi bond occurs with the p orbital overlap from that p orbital above and below the plane of these atoms. This central carbon also is sp2 hybridized, so it has that p orbital, allowing this to form 1 sigma bond and a pi bond. This carbon is predicted to be a linear geometry. There are 2 electron regions getting as far away as possible, and this carbon is said to be sp hybridized, where the 2 sp orbitals, and then there are actually 2 overlapping p orbitals to form these double bonds. So this sp linear, this carbon is also sp linear. The overall molecule is linear.